Okay, welcome to Information Theory Lecture 36. This is the last lecture of the two-quarter sequence. And it's been a long journey. We've done 36 lectures. This seems like quite a lot. But maybe, on the other hand, it's also quite a little, because there are still many things that we haven't covered that we could easily do another 15, 16 lectures and still not have covered everything. But I hope that after today's lecture, you will feel fulfilled, at least information theoretically, and satiated. So today what we're going to be talking about, we're going to dive right in and talk about the Slepian-Wolf approach to compression, to network compression, and then talk about the broadcast channel, and then talk just briefly about general channels. We're not going to have a lot of time to do a lot of that stuff. Here's our collective complete set of readings that we have for the entire quarter, and then of course last quarter down here. I hope everybody has had a chance to do all of these readings. I think many of you have. I do want to mention a little bit on the. So this is our last lecture. It's not our last meeting. Our last meeting will be Monday when we have final presentations. And I think most of the instructions, I think most people have been tracking the instructions, but I do want to mention that. So I've looked at the time slots and everything, and basically there will be 15 minutes per person per presentation. So plan on 15 minutes, and that includes questions. So basically plan on talking for like 12 minutes, maybe 13 minutes at most, and leave a few minutes for questions. And since I think everyone will have, by that time, read all of the papers, also come prepared for questions. So you will see these presentations on these papers that you've now read. And this, I think, will benefit everybody. It will benefit the presenter because they will get a collection of diverse and sensible questions. Everybody will also understand all of the presentations and will get more enjoyment from Monday's presentations. And also the presenter will have a chance to, and maybe be prompted to or be jarred into thinking more deeply about the problem in anticipation of actually potentially receiving some deep or complicated questions. So I think that, I don't know, I'm happy with the way that worked out, although I would love to hear your feedback on how you like those assignments. So the remaining assignments, I'll just remind everybody, so we have this Friday at 5 p.m. The last round of one-page summaries of the assigned papers, so a lot of you are probably already reading them. So read them by Friday and send in your one-page summaries for each paper. Assignments are on the web. On Monday at 1 p.m., your final slides and your 4-page paper is due. No lates are accepted. Now the number of slides should be based on what you think is reasonable for a 15-minute or really a 12-minute presentation. Hopefully you'll rehearse it a little bit yourself. So I'm going to be keeping pretty strict time. So I won't allow anybody to run over the amount of time that you have allotted. And then also everybody has to do a 4-page paper. And again, only 4 pages, no more. You can do less, but no more. Don't break your record. This class is a great record so far. So final presentations are going to be Monday at 2:30 in this room. And then lastly, next Tuesday, which is a week from yesterday, your final graded assignments of the papers that you've presented. And at this point, you've all now graded the assignments, and I think everyone's being very generous. This is collusion, right? Everyone's being generous with each other's grades. What's that?
Unwritten collusion.
Handwritten collusion, yeah. So I think that maybe you've all sort of met outside of this class and say, hey, I'll give you 100% if you give me 100%. So, no, actually, not everybody gave everybody 100%. So somebody got a 99. So much for the grades. But okay, so any questions on logistics? Okay, so let's talk about Slepian-Wolf and then the broadcast channel. So Slepian-Wolf is again back to the compression strategy. So again, in compression, what we want to do is we want to take a source and compress it down to its entropy limit, and we want the rates of the compression, which is the number of bits per source symbol, to be as small as possible. And in this particular case, we want to compress 2 correlated sources, X and Y. And we know that we can do that if we can compress jointly by compressing it down to the joint entropy. So that's nothing new. It's basically just it's a two-element vector random variable. But what Slepian-Wolf encoding does is essentially a form of distributed compression. So the idea is that each compressor has access only to X or to Y, not both. None of the compressors have access to both. And so we know that each compressor can compress down to the corresponding singleton entropy, either X or H of X or H of Y. But we know that if they were to just do that naively, and if the variables are very correlated, then it's potentially the case that the overall rate, which is H of X plus H of Y, is going to be much worse than the potential rate that you could get if you were to do joint encoding, which is H of X comma Y. So for strongly correlated variables, this is potentially very bad. So the question is, how can one take two sources which are correlated and compress them without actually communicating during the compression process? In other words, you can't look at X when you're compressing Y, and you can't look at Y when you're compressing X. But how do you do that compression in a way that you can still compress down to the entropy, the joint entropy rate, H of XY, without any communication during compression? And what Slepian-Wolf showed is that, in fact, even though this seems, at least when you first think about it, counterintuitive that it would be possible, they showed, in fact, that it is possible. It's possible to do separate compression for each of the sources, and the compressions are done independently, even though the sources are correlated, and you can still compress down to the entropy limit. How can this be? So indeed, it seems counterintuitive. So we can't jointly compress. So we can't use Y, we can't condition on Y when we're compressing on X. We have no idea what Y is. We've only got access to X. And similarly, we only have access to Y, not knowing X. So one thing we could do, we could compress X down to, we could compress this to this, X to H of X. And then let's say that we just know this rate, Y to H of Y. So in other words, we know that H of Y given X is less than H of Y. And we could compress potentially Y down to H of Y. But if we were to do that independently, that would be either errorful or difficult or problematic. It basically, if we were to just naively compress Y down to H of Y given X, that would be below the entropy rate of H of Y, and we would therefore get errors. But the question is, maybe there must be some way of doing it, or maybe there's some way of doing it, and that's essentially what we're going to show how to do. So here's the key visualization of how it works. So we've got this X and Y, which is correlated here. And we've got one encoder for X and one encoder for Y, and then we've got this joint decoder here. Now that's the key thing, as you'll see, is that it's joint decoding. That the decoder is not going to be independent. The decoder has access to both what's coming out for X and coming out for Y. And the magic here really isn't magic, it's just that the decoder actually happens to be able to get access to both compressed sources. So each of the encoders, however, has access only to the corresponding inputs, either X or Y, not both. And then the decoder's job is to construct the original X and Y. So the decoder's job is to come up with some estimate of X hat, Y hat, which is a good proxy for X and Y. Everybody get the setting? Okay, so okay, good. I thought I was missing a slide. I have the slide. Okay, so here's some. Sometimes I don't look at the titles of these slides. This is some very unsurprising at this point definitions. Hopefully these will be very unsurprising. So we define a distributed source code. It's for rate R1, R2. So we have a sequence of 2 to the nR1, nR2, comma n source codes for this joint source XY, which consists of 2 mappings. F1 maps from the X alphabet to an integer that ranges depending on the current rate, R1, and F2 maps is the same thing for Y1. And it corresponds to a message, W1 and W2. That's the compressed version. And basically we need to, W1 takes nR1 bits, right? And we're measuring the number of bits per source symbol, which is just R1. And what the decoder does is it takes these two integers, both of them together, and comes up with a candidate for x and y simultaneously. Now this is really the key, is that we still get to do joint decoding. It's not like we take W1 and map to X1, and then independently take W2 and map back to X to Y. Sorry. We take W1 and map to X, and then separately take W2 and map to Y. We're not doing separate decoding, we're doing joint decoding. So because of the fact that we're doing this mapping here, joint decoding, that's really the key. That's the thing that makes it possible. So the question is, can we do clever encoding of the two sources such that it makes it possible for the joint decoder to recover x and y, and at the same time the rates of the codes are such that we can get down to the joint entropy, h of x comma y. So does it seem less counterintuitive now when you think about it that way? First it seems very counterintuitive, and then you say, wait a second, maybe it's not so counterintuitive. We have a probability of error. So this is the standard thing where if we encode the two sources, f1 of x and f2 of y, and then we decode by g, we've got a probability of it not being equal to the original source sequences, which is this stuff here. Okay. And the notion of achievability is also pretty standard at this point, right? Anybody need any view of this? Basically, if there exists a code whose probability of error goes to 0 as n goes to infinity, then basically the rate pair R1, R2 is said to be achievable. And so here's sort of the kind of thing we've got. So again, we have a two-dimensional space within which one can talk about achievability or non-achievability. We have an outer bound based on a certain set of constraints. I mean, first of all, this yellow region here on the right is sort of a simulated, the yellow band is sort of the achievable region. So presumably anything in that yellow band is possible. Two rates within there are possible to do. The outer bound, let's do the outer bound first. So the outer bound basically says that, well, definitely even when you're doing joint decoding, R1 can't be less than h of x1 given x2. So we have to be to the right of this, which gives us this guy here. And similarly, R2 has to be greater than h of x2 given x1. So we have to be greater than here. And then similarly, the two rates together have to be greater than the joint entropy, which gives us this thing here. So basically, anything out of here, if we take a point there, or there, or there, that's definitely going to be not achievable, because we can't even achieve those if we were to do joint decoding. Right? When we're doing joint decoding, is that clear? I mean, in particular, like this stuff here, why can't we achieve any of that? Because even if these things are correlated, right? Even if we know x2, we can't compress x1 down to something less than h of x1 given x2. Now maybe if there was something else that we could utilize, maybe we could compress it down, but nothing else is available. We only have x1 and x2. And so in such case, the lowest we can compress x1 down to is the entropy of x1 given x2. And similarly for entropy of x2 given x1. Now the inner bound is basically sort of a naive inner bound. It says, okay, well if we were to just do separate encoding, we say, okay, well let's compress x1, which can compress down to h of x1 separately, and compress x2, which can compress down to h of x2 separately. So basically any point here is just easily achievable by just independent encoding. Right? There's no communication necessary. So the question is this region in between, where the boundary between this yellow stuff here, what is the boundary? Where is the boundary between achievability and unachievability? And that's what we want to understand. Everybody get the idea, the picture? Okay, so the inner bound is achievable, but we want to do better. The outer bound clearly can't be improved upon. That's the best we can do. Now what we're going to show, in fact, is that the Slepian-Wolf theorem and the corresponding coding and decoding algorithm shows that the outer bound corresponds to the achievability region. In other words, this is the picture that we've got. Now this seems pretty nice, right? And again, the question is, how is this possible? But as we will see, it's going to depend on smart encoding, separate encoding, and then smart decoding, joint decoding. So here's the theorem. The achievability rate, this is just basically expressing the constraints that correspond to this yellow region. The achievability rate region for this particular setting is given by this set of inequalities. Okay. So the way to do this is that we need a new coding procedure, and this is pretty neat. And so to introduce this coding procedure, we're going to talk about it first in the context of just regular, not joint coding, but singleton coding, just to show that we can still get the same rate that we get when we're doing regular single source entropy compression. And the idea that was introduced by this paper, which is still quite celebrated, is this idea of random binning. So it's not exactly the same as the Shannon asymptotic equipetition property procedure that we saw before. And the proof technique is still very much Shannon-like, but the way that you do the encoding, and again, it's an existing proof. It's an existence proof. It says there exists a code that achieves these rates, and if you have these rates that satisfy, if the error goes to 0, then the rates must satisfy these constraints, and if you have these rates, there exists a code that actually gets those rates. So it doesn't give you a code, but it uses typical set-ish like stuff. But then the new idea is this random binning. And let's talk about it for a single source. So we've got a rate R. Okay, we have 2 to the nr bins, integers. And what we do is we randomly assign a given sequence to a bin. So we have all possible sequences, x of 1 through n, and each one is randomly assigned to a bin with replacement. Okay. And we do this for all such source sequences. So that means that we have bins assigned for the typical sequences and for the atypical sequences for any given n. Because we're using it for all cardinality x to the n possible sequences. And again, it's with replacement. So all sequences are binned, not just the typical ones. So the notion and this is the critical idea, so the notion of typicality is not needed at the decoder. And this is critical because the decoder doesn't need to know what's typical and what's not typical. It's only did I say the decoder? The encoder doesn't need to know what's typical and what's not typical. It's only the decoder that ends up needing to pay attention to that. And of course, these things, being that they are correlated, there will only be those things that are jointly typical ultimately that happen. But the encoders don't need to know what's typical and not typical. So they just go ahead and blithely have a bin associated for every possible sequence. So that means that for each x, we draw with the replacement a random w. That's the index bin. Okay? So we have some mapping. We've created this random mapping. So once the random binning is done, we have 3 possible states that each bin can be in. Okay? And this is a random outcome, but once it's done, the outcome of this random experiment is that each bin could either be such that A, or 1, I should say, there's no typical sequence assigned to this bin. Okay, so in other words, this case means that no typical sequence is assigned to this bin, and 0 or more atypical sequences are assigned to that bin. Okay. Now again, the random binning didn't pay attention to the typicality or not. It's just saying that this is what happened. I mean, there are some sequences are typical, some sequences are not typical. The bin could be either in that state, or the second possible state that could happen is that only 1 typical sequence is assigned to the bin, and 0 or more atypical sequences are assigned to the bin. But the third one is that more than 1 typical sequence is assigned to the bin, and again, 0 or more atypical sequences are assigned to the bin. There's 3 possible cases. So which case do you think is likely to be the one that yields non-error?
Non-typical.
Sorry?
The second one.
The second one. Is that what you said? Yeah, the second one. So case 1 and case 3 are not going to be good if it ends up that we receive a sequence in either of those states. Okay. So what we do is to encode we have a sequence and we just replace it by its bin index, and the rate of the code is r. And then at decoding time, what we do is we receive an index, and we look at the corresponding bin. The decoder does know the typical stuff. The encoder doesn't. The decoder looks at the corresponding bin, and if it's the case that there's only one typical sequence in that bin, case 2, in other words, there could be as many atypical sequences as you want in that bin. But if there's only one typical sequence in that bin, you declare that index as the one that was sent. And if that was really the case, then it's correct. Otherwise, if there's case 1 or 3 occur, in other words, if you look in the bin and it's either case 1 or case 3, we declare an error. The question is, will this work? So we need to bound the errors. So again, we're using Shannon's averaging over all random quote choices. And so we get the probability of errors equal to the probability, this is the standard probability of error that we've been using for quite a while now. And so we get, by the union bound, 2 pieces of this error. First of all, the probability that x is not typical, which is always going to potentially be something that has some non-zero probability, but we can make that as small as we want. But we sort of treat that separately through the union bound. And then this next bit is the following. So what we're doing is we're summing over all sequences here. Okay. And what this stuff here does, it says it's the probability that there exists some sequence x prime which is not equal to x that's typical, and it was assigned the same bin. All right? Because if that ends up happening, because one possible error is that it's an atypical sequence, right? But that we know is going to go to 0. The other possible error is that we've got 2 or more typical sequences assigned to a given bin. And so assigned to a given bin corresponds to this bit here. Typical corresponds to this bit here, and 2 or more corresponds to this bit here. And so we can write that probability as, well, epsilon. Epsilon comes from this. And then we've got the sum, which is the same sum here. And then what we're doing here is we're just basically summing over all typical x prime that's not equal to x, and looking at the probability that the bin is the same. Good. And that's upper bounded by, we have epsilon again. We're summing over all x again. We can just sum over all typical sequences, and the probability that this is equal to that is going to be upper bounded by 2 to the nr, right? 2 to the negative nr. Because that's how many bins there are. Right? Because if we have one particular bin assigned, if we assign it uniformly at random, which is what we did, what's the probability of in the next bin of some other source sequence assigned to that bin? It's 1 over 2 to the nr uniformly. Because now that's that has now severed the index from the probability, and we can bring this out here. This stuff just sums to 1, so it goes away. And what we're left with is the size of the typical set, which we know. We have an upper bound on that from last quarter. And we've got this whole thing here, which then can be written as 2 to the 2 epsilon, right? As long as the rate is greater than the entropy, right, by some epsilon. Again, an epsilon can be made as small as we want, and if n is big. So the key thing is that this procedure now allows us to do this kind of random binning, and we still have an unboundedly small probability of error. We can make that as small as we want by making n, the block length, big enough. So how do we do this then to do joint coding, which is the Slepian-Wolf idea? So right, I guess this is just discussion about this. So the notion of typicality is needed. This should say not needed. Is not needed. Notion of typicality is not needed at the encoder since all symbols are given a code word, irrespective of their typicality or not typicality. And it's only at the decoder where the typicality, where you know, once you've got an index, do we need to use typicality to see whether or not you know, there's one or more typical sequences in that particular bin. The other indices definitely happen. And so, since typicality is not used, suppose we do have two correlated sources that are encoded separately. We can still use this random binning thing. Like we can random bin for X and random bin for Y, and we don't know. We're not using typicality. We don't know what's typical or not. And so it's only at the decoder side do we use typicality to jointly decode X1 and Y1 based on typicality. So let's see how that's done. So achievability, you know, has again an unsurprising definition. It basically says that the rate pair R1 and R2 is achievable if there exists a sequence of codes whose probability of error goes to 0 and goes to infinity. And so what we do is we have a rate pair, R1 and R2, and so we partition, or we have essentially 2 to the NR1 bins for X1, for X, sorry, and then 2 to the NR2 bins for Y. And what the encoder does is the following. So completely separately, for X, every possible sequence in X is assigned a bin uniformly at random. Right? So again, there might be overlap. I mean, you might it's with replacement. So there might be some bins that have lots and lots of code words, or sorry, lots and lots of source sequences assigned to that bin. It's governed by R1. So depending on what R1 is, it depends on how many bins there are. If R1 is very, very big, it's unlikely to happen. If R1 is very small, it's quite likely to happen. And the same thing happens with R2. We have this many bins for Y. Okay, so the bin assignments are done without recourse to typicality, but the bin assignments are known both to the encoder and decoder. The decoder is the one who gets to use typicality, not the encoder. And so what does encoding mean? So sender 1 basically sends or stores the corresponding bin number for a given source sequence, as does sender 2 for its corresponding source sequence, Y. And then what decoding does is that is the following. This is the critical bit. So we receive this pair, which is a set of indices, right? Or we're decompressing really. So we're decompressing. We've got two integers, and what we do is we decode this. This becomes the thing that we decode if there exists only one pair whose encoding was correspondingly I0 and J0. And these guys were jointly typical. Okay. So now the reason you know intuitively why this kind of thing works. I mean, you are encoding these things separately, right? X and Y are being encoded separately. But we know that as the block length gets big, the only thing that's really going to happen ultimately is that the jointly typical events are going to be the thing that have all the probability. Right? So what the decoder does is it says, well, I'm going to decode these guys if there's no indication of error, and if everything's jointly typical. Now the question is, does the probability of error then still drive down to 0 for large block lengths? So what that requires then is that there has to be one pair of sequences that have the right set of indices, meaning that you can't have like one bin that has two typical sequences in there or something like that. and they have to moreover be jointly typical. And note the presence of non-typical or atypical sequences within a bin don't matter. So here's sort of the error conditions. So the idea is the following. So we've got this picture, was sort of, hopefully it will elucidate and not confuse. So we have a source sequence X and a source sequence Y. And then this is all of the possible bins that X might be assigned to. This is all the possible bins that Y might be assigned to. So here's a bin, pair of bins, I should say. So in this particular case, we have two indices, and there were, if it's the case that we happen to receive those two indices, then that's an error because it's one or more pairs that are not jointly typical. The idea is that the solid dots are jointly typical. Okay. So that means an error. E0 is one error. Another possible instance of E0 is the case when we receive, there's an empty bin, and that's not likely to happen because we're doing compression and we've got essentially a set of integers, a pair of integers, and we've got these two integers. So something must have happened. Something was assigned to that bin. So this really doesn't happen. Right? The other thing that could possibly happen is another error is that there's two. You get an integer, you get a pair of integers, and there's two jointly typical sequences, pairs of sequences in there. So that's going to be an error. An instance of no error is this. So we get a pair of integers, and there's only one pair of jointly typical sequences in there. So that's good. Or we get a pair of integers, and there's one jointly typical pair of sequences, and there's other non-jointly typical or pairs of sequences. That's not an error. Because we know eventually that's never going to happen, or that shouldn't happen if the block length is big enough. I mean, the atypical sequences. The other possible thing that can happen is that, for example, this. Does anyone want to surmise what that might be? So there, what it would be is like we assign an integer for X, and for some reason there's some probability that two corresponding Y's are paired with that particular integer. So that's going to be an error. That's called E2. And then the symmetric thing, which is E1 here. So we have to account for all these different kinds of errors.
So why is it done with replacement like that?
It doesn't matter. It turns out it doesn't matter. So the point is that you can have multiple sequences in there. It's just a very, very easy binning scheme to do, and it's still the case that the error goes to 0. So in other words, never do anything stronger than you need to. So what's going to happen is you might have multiple things that are assigned to bin, but the idea is that if the rate is big enough, if the rate is good, then the probability of having two jointly typical sequences in the same bin is going to be very small, as we will see. It's going to drive down to 0. Now, the atypical ones you don't care about. Right? If you did it without replacement, you would need to account for all cardinality x to the n bins. We're only given 2 to the nr bins for each of R1 and R2. So there aren't enough bins for all of the sequences. What we want to make sure is that there are enough bins for the sequences that are going to occur. And the intuition also is that even if it's the case, I have a slide on this a little bit later, but even if it's the case that, let's say that you have your rate, let's say R2 is set to something like h of y given x. Okay, so the rate is set to something significantly less than h of y. If you were to do singleton decoding of y, this is a little bit getting ahead of ourselves. If you were to do singleton decoding of y, yes, there would be 2 or more, quite likely there'd be 2 or more y-typical sequences in a given bin. Why? Because you've set the rate less than h of y. However, yes, there are y-typical, more than one y-typical sequences in that particular bin, but what the decoder says is, oh, but what's the one that's jointly typical with the x that I got? There's only one of them. So you're cool. So, and that ends up being not a problem, because the decoder gets to use joint typicality, the encoders don't. And that's what I mean by it's key. The joint decoding procedure is what's critical here. So define events for each type of error probability. So let's do this for this picture. So we've got E naught, which is just this joint atypicality thing, where that we know doesn't happen eventually, very quickly. And E1 is where we have so remember x1 and y1 are the random things that are being encoded, and what E1 says is that there's some other x prime not equal to x that was assigned the same bin and is jointly typical. So that's bad. E2 is the symmetric version of that. It's where two y's are typical with a given x, jointly typical with a given x. E1 is two x's jointly typical with a given y. And then we have E12, which is where we have pairs. We have two or more pairs of sequences that are jointly typical. So that basically corresponds back to, getting back to this wonderful figure that corresponds to this guy right here. I don't know, is this a wonderful figure? It looks better when I've added all of these candy colors to it, doesn't it? And when YouTube, I really like it when YouTube chooses the thumbnail, and it chooses one of these really colorful ones. And everybody, I've noticed that the thumbnail videos that have colorful thumbnails are watched much more frequently than the ones that have bland thumbnails. So I was thinking, like, maybe I should put some sort of racy picture on each of these lectures, and everybody will watch information theory, and then they'll be sorely disappointed when they find out that it has nothing to do with whatever the racy picture was. Okay, everybody understand this? Definition of errors? So, so we've got random variables x1 and y1, and we've got random binning. We've got these probability of errors. The probability is all possible errors together. We just upper bound the error with the union bound, which is the same kind of trick that we've been doing. The atypical error goes to 0. No need to mention that anymore. E1, let's do E1, and then E2 is going to be symmetric, and in fact E12 is going to be almost the same thing. So the probability error is E1 is going to be is for every possible pair of sequences, summing over all of them, is the probability that E1 occurs with x1, x and y being equal to that particular value. And so what that is equal to is, you can say, okay, well, what's the probability? So x is a current value, and say, what's the probability that there's some x prime that's not equal to x, where x prime is also jointly typical with y, and that we're assigned the same bin, the probability that we're assigned the same bin. So we have the same kind of deal that we've got there. So we know that that has probability 2 to the negative nr1, because r1 is the rate for x1, right? It's the probability that another guy has come along, and because we're choosing bins uniformly at random with the replacement, the probability is 1 over 2 to the nr1. By the way, this is another reason why we use with replacement. It makes the analysis much easier. We wouldn't be able to use this probability if we didn't have replacement. This basically means that every choice is the same. It's not like the probability changes once we've chosen a bin, in which case we have to say 1 over 2 to the nr1 minus 1, because there's one fewer bin, and so on and so forth. It just simplifies the analysis, number one. And number two, it's sufficient. It's still the case that the errors are going to go to 0. So again, why do something more complicated? That complicates the analysis. When you can do something weaker, that still shows that the error goes to 0. This is an existence proof. It's not a guarantee. Okay, so then how many of them are there? Well, we just look at, okay, this is x prime not equal to x that are jointly typical with y. That's just the conditional joint typicality, the conditional typical set, which is this stuff down here. This is something we defined a few lectures ago. And we have the bound for that, which is h of x given y, or 2 to the n h of x given y. And so we get this whole thing is upper bounded by this bit down here. And that we know, as long as the rate 1 is greater than the conditional entropy, we know that that thing's going to go to 0 when n gets big. So E1, the event E1 is going to, the probability of that event is going to go to 0. As long as the rate 1 is greater than this conditional entropy. And a similar derivation, basically the same analysis shows that E1, E2 is going to go to 0 as long as, in that particular case, it's going to be rate 2 is less than h, rate 2 is greater than or equal to h of y given x. And then rate 1 plus rate 2 has to be greater than or equal to h of x comma y. So we've got those three constraints. So the converse of that's the first part of the theorem. The converse basically says that there exists a sequence of codes. If there exists a sequence of codes whose probability of error goes to 0, then the aforementioned rates, namely R1 has to be greater than h of x given y, R2 has to be greater than equal to h of y given x, and R1 plus R2 has to be greater than equal to h of x comma y, and those rates must hold if it's the case that a corresponding sequence of codes that has probability of error vanishing exists. And so the way we prove this is, again, Fano's inequality. It's amazing how much utility folks got from these tools that were first really sort of articulated by this 1948 paper. So again, here we are at the end of the second quarter, and we're still using a lot of these tools. It's remarkable. I mean, imagine doing something, coming up with a proof technique that is so universally applicable. Imagine doing that for your PhD. 60 years later, people are still talking about it in class. You can do it. You have the ability. Just be inspired and be creative. Think different, right? Be like Steve Jobs. Think different. Okay, so what we use Fano's inequality, and we're going to say that I naught and j naught are the corresponding random index that's been assigned based on the random source sequence x of 1 through n and y of 1 through n. So the binning is decided upon. The encoder and decoder are decided upon by the random binning procedure, which is this stuff. And here's Fano's inequality. And again, it's the same kind of deal. It's like we've got the probability of error between, this bit and this bit. There's the probability of error. We've got the alphabet size, log of the alphabet size, and then 1. It always takes the same form. Bring out a factor of n. We've got this stuff, and that becomes n epsilon. Where epsilon n goes to 0 as n goes to infinity. So, and then again, what we're going to do is we're going to divide by n, and we're going to be left with something goes to 0 as n goes to infinity. So, to show this bound, we show the bound on R1 plus R2. We go through this sequence of equations, and maybe I shouldn't even bother going through it because I think it's pretty straightforward at this point. And then what we end up getting is that the sum rate has to be greater than or equal to the joint entropy plus the epsilon, which goes to 0. So it basically puts a constraint, just like all of the cases. It says that if the probability of error goes to 0, it puts a constraint on the rates, thanks to Fano. Fano and the information theoretic quantities here, which at this point we know and love. And without going to further details, we can also bound R1 and R2 the same way. So it's the same proof idea as Shannon, and what was new is the random binning. And the typical decoding is still the same. Right? And you can generalize this to more than 2 sources quite readily by using joint typicality. Here's the theorem, which we're not going to prove, but I think it should be pretty straightforward. So we have V is a set of m sources. We've got this joint distribution, and what we want to do is each one of these sources we're encoding separately. then what are the achievable sets of rates? So a given rate vector is a set of, well, that should not be m, it's r sub m. But a given rate vector is basically a set of rates that, and the theorem states that if the rates satisfy this exponential set of inequalities, then we're good. Then there exists a sequence of codes whose probability error goes down to 0. So remember, R of S. This is basically why is this an exponential set of inequalities? Because basically we're saying for all subsets S of V, this must hold true. That R of S, which is the sum rate, the sum of the rates corresponding to the indices given by S has to be no less than this conditional entropy. In this case, it's the entropy of x of S, the random variable is S, given everything else, the complement of x of S, which is x of V except for S. And here's just this definition. So x of S is really just a set of random variables. So remember that figure. I mean, I'm not going to go back to that figure, but you can look at it. But remember the figure looks something like this. And we said that this was the achievable region. So it's basically a multi-dimensional version of that. Now let's look a little bit about this. Talk a little bit about this function. So we've got f of s, which is now a set function, which is equal to this quantity, this conditional entropy. And so the above constraints really sort of define this polyhedron, which can be defined in this fashion. It's basically P of F, which is all rate vectors, so all R in Rm, so this is m-dimensional space, all rate vectors, such that for all subsets of V, we must satisfy this inequality, where R of S is again the sum. So now the other thing to note is that this function, f of s, which is it's a conditional entropy, this is equal to, using the definition of conditional entropy, it's equal to the entropy of all the random variables minus the entropy of just the complement. And so this part here is just a constant. Right? It's just a constant. It's not a function of s because we're using all random variables. So this is really just this constant minus this complement. Now it turns out, interestingly enough, that f of s in such case is what's called a supermodular function. It's sort of like the negation of a submodular function. It's a supermodular function because it satisfies this inequality. Supermodular, this is less than rather than greater than. And this polyhedron actually turns out to be identical to something that occurs frequently in cooperative game theory. And P of F is also known as the core of a convex game. And it's an interesting parallel. This was understood back by game theorist very famous game theorist named Lord Shapley in 1969, 1970. Okay, again, come next quarter if you want to hear more about this. But I thought this was an interesting connection. Here's a little bit more on the intuition. By the way, are people satisfied with this? Do they get the intuition? Because if people are satisfied, I could take a break now and not do these intuition slides. Raise your hand if you'd like to hear a little bit more intuition. Yes, yes, yes. Okay. So here's the thing. It's a little bit what I was saying a little bit earlier. So we can easily encode x in this way, right? Because x, if we just know about x and we know the entropy of x, that's something that's easy to do. That's achievable. And if we were to sort of independently encode y using h of y given x bits, then if that's done, we're going to get an error. Again, for the same reason I mentioned before, because what's going to happen is that we're going to get more than one we only have 2 to the nr bins. And R2 is going to be small. R2 is going to be like equal to the entropy of y given x. So R2 is going to be small. So we're not going to have a lot of bins. We're not going to have enough bins for all the y typical sequences. So that means that there's going to be more than one y typical sequence inside of a given bin. Now x1 is not going to have that problem, right? Because x1, as we've encoded using h of x, a rate no less than h of x, and so we're going to have 2 to the nr1 bins for x. And so the only thing that's going to happen, because we've got enough bins on average, is that there's only going to be one x typical guy in all of the x bins. But this is where the potential problem lies. So it's almost certain that 2 typical y coders land in the same bin. There's just not enough bins because they're using too small of a rate. But the critical thing is at the decoder side, we get to condition on x. So yes, maybe there's a bin on the y side that has 2 y typical sequences in it, but as soon as we condition on x, one of those y typical sequences ends up not being jointly typical with x. So we can eliminate that from consideration, and what we're left with is only one y typical sequence, the one that's jointly typical with x, with particular x. So again, joint decoding has saved us. But at the same time, our rate is basically the sum of this plus this, which is equal to the joint entropy. So another way of looking at this is with clouds, and this isn't like cloud computing, this is the old-fashioned use of the word cloud, where we have clouds corresponding to sort of regions within which things are encoded. And there's a picture of this, I think, here, right? So like, conditioned on a given x here, there's only a much smaller set of y's that are jointly typical with a particular x than the full set of y's, which are just y typical. So this whole thing that I'm outlining here is all of the y's, but this bit in the middle, which I've outlined in yellow first, is the only thing that's jointly typical, and there are many fewer of them. So that's why it works. So one last thing I want to mention about this is that the Slepian-Wolf coding is really dual to the map channel. So it's like sort of the opposite. So remember the map, we have p of y given x1, x2, and here we have, so this is dual to that, interestingly enough. And the next thing we're going to do is study the broadcast channel. But before we do that, let's take a short break, unless there are questions. Welcome back to the second part. And the next thing we're going to talk about is the broadcast channel. The broadcast channel is another important channel where there's one sender and many receivers. The idea is the following: that there's sort of one channel that everybody sort of shares, or all of the receivers and the sender sends. And it's one possible case is that there's sort of one message that the broadcaster has for everybody to receive, or it might be the case that the broadcaster has a separate message for each receiver, or it might be some combination of the above. We're not really going to be considering the privacy aspects. All we're interested in is sort of rate possibilities. What rates can be achieved between the one sender and the multiple receivers. Now, before you want to sort of understand, so our goal is to understand the limits of achievability of rates. So here's an example of these scenarios that you might have. So let's say you're a cell phone tower. So you're a broadcaster and you have lots of cell phones which are receivers. So in that particular case, it's the same channel. But the idea is that the broadcaster is transmitting something over that same channel, each message of which is sort of ideally destined only for one receiver. Another receiver shouldn't ideally have access to a message intended for the first receiver. But there's another type of broadcast channel, and we happen to be in one right now, which is that I'm trying to communicate to you. I'm a broadcaster, And in our room, this room is a broadcast channel, and hopefully you are all receiving the same message that I'm broadcasting. So that's essentially what the goal is of a good teacher. And actually, to be honest, the goal of a good teacher is to broadcast and to teach in a way that all students receive useful information. And in other words, not to say that there are such things as a bad student, but you might have different students at different levels, say. And so, students at level 2 and students at level 1. And you want the students at level 2 to receive something always and to learn something, but at the same time, you don't want to only address students at level 2, you also want to address students at level 1. So you want to somehow manage to sort of convey information for both. I think another great example of this, actually I should say that any time we fail, this is the teacher's fault, of course. But another great example of this, which I've actually only become familiar with recently, is the idea of family movies. And because I have children now, and my children like to go see family movies, and of course I am not particularly interested in Bob the Builder, but the best family movie is one, it's a broadcast because it goes to parents and children, but it has something that on the one hand sort of is funny and entertaining to the parents, but at the same time is funny and entertaining to the children without there being interference between both. So in other words, the parental jokes have to somehow not get in the way of the children's entertainment. So that's an example of a broadcast channel as well. So here's our model. It looks like this. We have the idea of, in this particular case, we've got two messages, W1 and W2, which gets encoded onto one single channel. The channel looks kind of like this. We have X as the input, and then Y1 and Y2 is the output. And then W1 is the intended message for the first receiver, and W2 is the intended message for the second receiver, which has each gone through a corresponding decoding procedure. Okay. So a couple more definitions. We have two receivers. The information in the particular setting that we've got is such that the information is independent. And so there we have this corresponding channel where we have P of Y1 and Y2 given X. And we have this particular setup where we have a blocks of length n and it's memoryless again. And we have a code sequence, which is a sequence of codes. And this is also just fairly general, that we have an encoder which basically takes two messages, one at rate R1, another at rate R2, and comes up with a channel message, which then gets broadcast out. And what the decoder does is it takes the corresponding received message for Y1 and comes back with a version of the message for receiver 1, and similarly for receiver 2. We have a probability of error, which basically says whether or not the received symbols were not the ones that were sent. And the notion of achievability is also pretty standard, where we say that rate 1 and rate 2 is achievable if there exists a sequence of codes whose probability of error goes to 0. Now here's something else that we're sort of separating. We're saying that W1 and W2 are independent. It might be the case that there is some common information that's meant for all of them, for both receivers. And so what we're going to do is treat these things as separately. So W0 is the message that's sort of meant for everybody. Like if this was a family movie, maybe W0 would be roughly the plot. Has anyone seen the Lego movie? This is the one I'm thinking about. Raise your hand if you've seen the Lego movie. All right. So you've seen the Lego movie, great. I've seen the Lego movie. So the plot, the rough idea of the plot, which is that President Business is trying to keep you from being creative with your use of Lego, is W0, right? The subtle parental innuendo jokes might be W2, and the real silly action, colorful stuff is W1 for the children. Does that make sense to anybody? No, maybe it makes sense to you. If you've seen the movie, you've got to see the movie. If you see the movie without having children, then basically you're interested in W0 and W2, not W1. And so in such case, we've got a code sequence for a broadcast channel. which is basically a sequence of 2 to the NR0, 2 to the NR1, and 2 to the NR2 encodes. And so the idea, again, is that now we've got an encoder which takes a message intended for both receivers, a message intended for the first receiver, and a message intended for the second receiver. So we're separating them to have different rates. And that gets sent into a channel sequence, a channel input sequence. And then we've got a decoder for receiver 1, which decodes and tries to get back the common message and the specialized message. And similarly for receiver 2, tries to get back the common message and the specialized message, except that the specialized message for receiver 1 has a very different rate, potentially, than the specialized message for receiver 2. And then we've got a probability of error. In this particular case, the probability of error, we get an error if either receiver doesn't either get their specialized or their common message. And without loss of generality, we can assume that all these guys are independent and uniformly distributed. And the notion of achievability, a rate pair is achievable if there exists a sequence of codes with probability of error going to 0. And a rate triple is achievable if the same thing happens for that triple of rates. The capacity region is the closer of all achievable rates. Okay. Everybody happy with the setup? Any questions on the setup? Okay. So the first theorem is to say that the capacity of region of the achievable rates, this is in the R1, R2 case, depends only on these conditional distributions, P of y1 given x and P of y2 given x. So why is that? Let's sketch the proof. But basically, when we look at y1, or respectively y2, the error, the actual error, really only depends on the joint distribution between x1 and y1, or x1 and y2. Those two corresponding errors, right? So let's define a number of quantities. This might seem a little counterintuitive at first. Let's go through this a little bit. So we define A, which is the event that either receiver 1 or receiver 2 was an error. B, which is the event that receiver 1 was an error. Or B2, the event that receiver 2 was an error. So B1 or B2. Right? So if B1 was an error, if receiver 1 was an error, that means that one of them was an error. So we have this implication. And similarly, if receiver 2 was an error, that means that one of them was an error. And so what that means is that, you know, one of the events, the singleton event error, means that the either or error event is true. So one of them has a smaller probability. In fact, we have these probability bounds. So the probability of the event B1 is going to be no greater than the probability of the event A. And similarly for the probability of the event B2. Everybody with me? Including those who are twittering?
What hashtag should we use for this stuff?
Fantastic, amazing lecture. Great jokes. Full of himself professor. All of those things are applicable. What we then have is that the maximum of the probability of B1 and B2 is less than the probability of A. But also, from the union bound, we also have that the probability of A is less than the sum of the two corresponding event probabilities. So in other words, we've got, I hope this notation isn't going to be confusing, but we have that thing which I've just highlighted in green. So we've got the max of the two probabilities. Why did I change the notation in the middle of the slide? I don't know. But basically, what is this? This is supposed to be the probability of B1, and this is the probability of B2. This is the probability of A. This is the probability of B1 is the probability of B2 again. Okay? Just in case you're wondering. So the max of the two probabilities is less than or equal to the joint event probability, which is less than or equal to by the union bound. the sum of the probabilities. So now this is the error, the 1 plus 2 probability, which is really equal to, this is the probability of A. So that thing does depend on this full joint to drive down the error. It's both necessary and sufficient to drive down these B1, B2 probabilities for this joint probability to drive down. So in other words, the left-hand side says, the right-hand side says it's sufficient, meaning that if you drive down both the probability of B1 and B2, then you're driving down the probability of A. But then the left-hand side says that if you're driving down the probability of A, you're driving down the max of the two probabilities, so you're necessarily driving down both. So therefore it's necessary, which is from the left-hand side, and sufficient from the right-hand side. The left-hand side, in this that's not clear, here's the left-hand side, and the right-hand side is this. It's both necessary and sufficient to drive down both of these probabilities individually. And so therefore, each one of these are essentially all that matters for the actual probabilities of error, and therefore the achievability rates. Okay, so that's done. Any questions on this? So now if we've got a broadcast channel, we're going to define the two singleton capacities, Cj, which is this stuff. And we've got these two sort of marginal conditional distributions, P of y1 given x and Py2 given x. Now if we just do this, we can again use time sharing, like we did in the Mac, and we can essentially achieve any sort of rate pair between these two capacities. And that's going to then give us a very, very simple inner bound on the capacity region of the broadcast channel. But on the other hand, we definitely have this upper bound, right? Because we know that we're not going to be able to communicate greater than the mutual information, the max over P of x of the mutual information between x and y1 and y2, because that's the joint bound. That's the case that y1 and y2 are sort of considered together. So that gives us an outer bound. And neither bound in general is tight. So here's an example of what we've got. So we know we can achieve this point, right, by turning off communication to R1. And we know we can achieve this point by turning off communication to R2. We know we can, by time sharing, achieve any point here, right? We also know that we can never communicate greater than this for R2, we can never communicate greater than this for R1, and we can never communicate greater than this for both. So that gives us the outer bound. So the question is where, again, just like before, where in this inner region does the true boundary lie? That's what we're trying to figure out. And if you're wondering, that's why there's a question mark here. So, oops. Okay, so here's one sort of nice idea that actually for this particular version of the broadcast channel turns out in fact to be tight. So we might actually have one receiver, maybe it might be cleaner or stronger or allow for a greater rate than the other. Okay, so let's sort of see how that actually works then. So what we can do is then have the weaker receiver recovers its message at the rate which is given by whatever the weaker receiver's rate is at, meaning it's going to be less than the rate for the stronger one. And what the stronger receiver does is it recovers its intended message by first recovering the weaker message and sort of canceling that weaker message out, and then in some sense cleaning up the channel. Because remember, it's a broadcast, it's the same channel. So if I'm sending a message to both of you guys at the same time, they potentially are interfering with each other. One person's message might be seen as noise to the other person. One receiver's message might be seen as noise to the other receiver. But I might be sending information out at different rates, and so what the stronger receiver, the one who's receiving stuff or has the capacity to receive stuff at a higher rate, is decoding the weaker receiver's message and subtracting that out and getting back their message directly. So in some sense, that means that this is, again, we're not talking about privacy here. We're not saying that these messages aren't, the weaker receiver would only get their message and the stronger receiver would get both messages. So we're not dealing with privacy at all. We're just talking about the achievability of given rate pairs. So let's do this in the following setting. We have two BSCs, BSC1 and BSC2 with different probabilities, and let's, without loss of generality, assume that P1 is less than P2. So remember, the BSCs with the given P's these are the crossover probabilities. These are the probabilities that there's going to be a bit flip. So if we send a 0, it's going to be received as a 1, or if we send a 1, it's going to be received as a 0. So a stronger channel, a less noisy channel, is going to be the one that has the smaller probability, which is P1 in this case. And we're assuming that both are strictly less than 1/2. So here's the setup. We've got X. So remember, it's the same thing being sent. It's the same message being sent to the channel. When it goes to Y1, we assume that it's sort of it's corrupted by, a Bernoulli channel with probability, or I should say a symmetric channel with probability P1. So you can think of it as like a modulo 2 arithmetic of adding Z1, which is just a bit flip with probability P1, and this is a bit flip with probability P2, go to Y2. So treating these things as independent, right? We know that we can, again, do time division. We can get this point by essentially turning off R1, or turning off receiver 1, getting this point by turning off receiver 2, and we can get any point in the middle by time division multiplexing. But we want to do something better. We want to do something like that. So the question is how? Can we do better? What do you think? Using a simple encoding procedure. So here's how we do it. This is something called superposition coding. And what it is, it uses auxiliary random variables. It's kind of a neat idea. So we're going to let U be a Bernoulli random variable with probability 1/2. And let V be a Bernoulli random variable with probability alpha, where alpha is between 0 and 1/2. And U and V are independent. Okay. And X, the thing that we end up getting sent, is going to be U plus V mod 2. So in other words, we write this as this. So we choose the rates that we want, R1 and R2. And what code generation is going to be the following. So we're going to randomly generate 2 to the NR2 sequences of this form. So we've got a message. Let's say W2. W2 is the message that we want to send to W2. So U essentially becomes the code word that is meant to encode the information that's given by the message W2 for receiver 2. And we have a set of possible messages that could be sent, no more than 2 to the NR2 of them, because that's our rate, R2. And then these messages, these code words are chosen uniformly at random, basically based on Bernoulli fair coin flips. So again, the idea is that we have 2 to the NR2 possible messages we want to send. We flip a coin 2 to the NR2. For each of the 2 to the NR2 messages, we flip a coin, a fair coin, n times. And that gives us this code word. Now these are going to be, as we're going to see in a minute, cloud centers. These are going to sort of define clouds. And what the receiver is going to do is only decode which cloud it is. And then receiver 1, the stronger receiver, is going to, in some sense, decode not only which cloud it is, but also which water particle within the corresponding cloud it is. So the cloud identity is going to be the thing that represents the message that is intended for receiver 2. And the water particle within that cloud is going to be the thing that represents the message that's intended for receiver 1. And so receiver 2 only needs to decode the cloud identity. Receiver 1 needs to encode both the cloud identity and the water particle in that cloud. So basically, receiver 1, like I said, gets the message for receiver 2. Whereas receiver 1 only gets his or her message. Receiver 2 gets only his or her message. Receiver 1 gets both messages because it gets both the cloud identity and the water particle. Okay, so then we're also doing code generation. So we're going to get essentially a code word for every possible message that R1 wants to send. Okay, so here's message W1, and we have a code word V1. So now the question is, we want to send both W1 and W2 out on this broadcast channel. So what do? We take the sum, mod 2. So this bit here is what actually gets sent out on the channel. So it's some combination, it's this combination of both. So somehow, or another, I mean, basically, like I said, both messages are sent out on the same channel in this way that's seemingly somewhat convoluted, but maybe it's actually recoverable. In fact, we're going to see that it is. We need a decoding strategy, which is something that has probability of error going to 0 if these rates are respected. So receiver 2, all receiver 2 needs to do is recover his or her message, which is W2. Right. So what does receiver 2 receive? Well, receiver 2 receives this. It's basically receiver 2 receives this whole thing, which was sent. Right, that was the thing that was sent out on the channel, and then we've got the VSC, that particular noise pattern, Z2, which is also adding to it mod 2. So that's then the receiver, and you can look at this as basically here's the message that is intended for receiver 2, and it's been corrupted by noise that looks like this. So again, in this particular case, the message for W1 is treated as noise, and then the combined noise consists of the message for W1 and the channel noise. So this is the combined noise. So this can be seen as sort of greater noise. So the combined noise is greater than the noise of the channel. Does everybody get that idea? Or does everybody think about springtime? Okay, so now this is doable. I mean, as long as it's the case that this combined noise, this greater noise, is not too great, then from the capacity of the BSC, we know that we can communicate with vanishingly small probability of error as long as the rate for 2 is not too great. And the rate for 2 not being too great means that it must not be greater than 1 minus the entropy of the channel given by the combined noise. Now the combined noise is sort of this strange thing where we're using alpha star P2. So it's sort of like a convolution-ish kind of thing. So it's alpha times 1 minus P2 plus 1 minus alpha times P2. Now why is that the right thing? I think probably a little picture would probably best explain it. So we have 0 and 1. So it's a cascade channel, right? So in the first case, you've got this. Which one should we do first? So this is alpha and 1 minus alpha, 1 minus alpha. This is 1 minus P2. So the effective noise is basically either, it's the probability of a bit flip. It's either this path, oops. It's this path here, which is alpha times 1 minus P2, or this path, 1 minus alpha times P2. So the way of getting, it's the way of getting from this guy to this guy. Here's the bigger version of the picture. Does that look better? Now you can pay attention. I see it bigger on my iPad, you don't. But there it is. So basically it's the way of getting from this guy here to this guy here. So that's what gives us this stuff down there. So it's the effective BSC for that particular channel. Now what happens with receiver 1? So receiver 1 is the cleaner one. And we're using this idea of successive cancellation decoding. So this is very similar to what we did for the MAC channel. So again, we receive the same message. We receive Y1, right? And in this particular case, it's, oops, let's make this a little bigger. It's this. Well, it's actually, we receive the message, the channel output for receiver 1. In this particular case, we've got U, which is the message that was intended for W2, involved with all of this stuff here. So this is the message for receiver 1. This is the message for receiver 2. So the first thing that we do is we cover W2. So receiver 1 recovers the message intended for receiver 2. And we treat the aspect of the code word that was sent to receiver 1, namely its own code word, we treat it as noise. And we're going to see, the assumption is that the rate is going to be able to handle this, and I will say how that works in a second. So once we've got W2, let's say we've gone ahead and we've decoded W2, then we come up with a new message. So, which is Y1 hat. So it's basically the original one, which is here. And then we once again add the decoded message for receiver 2 in. And what ends up happening by the properties of log2 arithmetic is that this stuff cancels out that, and that cancels out. And what we're left with is a cleaned up version of the code word intended for receiver 1. So then what we do is, with that cleaned up message, we go ahead and recover W1 from this cleaned up guy here. So what must happen? So the probability of error goes to 0 as long as this is true, as the sum rate is less than or equal to 1 plus P1, right? So the two rates together, because remember, we're sending both messages to receiver 1, right? And we need to be able to recover both of them. And P1 is the BSC for receiver 1. Right? So we get this. I mean, this ends up being true if since rate 1 is going to be less than or equal to the mutual information between x and y1, which based on what we've got, based on how we've done this, it's basically the mutual information between v and v XOR z1, which is equal to the difference of these entropies. Right, now the entropy of v XOR v1, v XOR z1, is just basically equal to the entropy of this convolution. So it's alpha convolved in some sense with P1. And then once we've got V, once we're conditioned on V, the residual entropy is just the entropy of Z1, which is just H of P1. So what we end up having is that as long as this rate is less than or equal to this bit, and R2 is less than this bit. Now, the stuff that I just outlined in green, if we add up R1 and R2, then what's going to happen on the right-hand side is that this is going to cancel out, this is going to cancel out. The rate is going to be less than 1 minus h of p1, which is going to satisfy this constraint here. Okay. Now, the last thing that we need to make sure about is this condition here. And that we know is true because we've, first of all, assumed that P1 is less than our P2. And we choose R2 so that this is true. That R2 is less than 1 minus h of alpha convolved with P2, which implies that R2 is less than 1 minus alpha convolved with P1. So therefore, we've got it. So this leads to this new inner bound, which is here we go. And in fact, that's better than TDMA. So the bound of the superposition coding is this sort of round region, and the TDM guy is the line. So we can then do better broadcast coding in this case, using this coding strategy. Any questions? The only tricky thing about this is this stuff here down at the bottom. If you understand that, you're in great shape. So here's the cloud view, since we all like clouds, especially in Seattle. We have 2 to the NR2 clouds, and within each cloud, so 2 to the NR2 clouds, remember the cloud identity is the thing that corresponds to the message intended for receiver 2, and within each one of those clouds lies 2 to the NR1 code words. So U, or namely this code word for W2, is the thing that indicates the cloud ID. The total rate is R1, R2. So right, the total number of water particles, the whole number of things altogether is going to be R2 to the NR1 plus R2. But receiver 2 only distinguishes between clouds, not the code words within the cloud. So here's the picture then. Oops, what's going on here? Here's the picture. So the big thing is the cloud. It's all this stuff here. And then within, so basically, the only thing that R2 needs to discern is, oh, this is the cloud. I mean, that's the cloud ID. And once I've got that, I can recover the message intended for receiver 2. But receiver 1, which basically is at a rate of R1 plus R2, needs to discern which, in some sense, satellite code word, or what I was calling water particle within the code word, water particle within the cloud, it was. And so receiver 1 identifies both this pink region and the green thing I just circled in green. And the trade-off, you can sort of trade off within the constraints that, R1 and R2 must be less than the joint capacity. You can either have fewer clouds, which means that receiver 2's rate decreases, but then if you have fewer clouds, you have more particles within each cloud, which means that receiver 1's rate increases. Or you could have more clouds. This is the cloud description, remember? You have more clouds, and the clouds are smaller. The total cloud density, the total number of particles, water particles, is the same. But the question is, how do we partition the water particles into different clouds? Do we have large clouds with many water particles, and therefore few clouds, or few clouds with few water particles and therefore many clouds? That's the trade-off between the two rates. Each cloud has this many code words. The 2 to the NR2 clouds. This is essentially what I'm saying. There's a total of 2 to the NR1 plus R2 code words, which corresponds to 2 to the NR1 plus R2 water particles. The cloud radius is controlled by alpha. How noisy is that going to be? And this is this trade-off I mentioned. Is the trade-off kind of clear? What's going on? This picture a little bit clear? Okay, so it turns out that for this particular channel, that ends up being tight for that particular scenario, not the one I just showed you, but the one of the binary symmetric channel case, that coding strategy ends up being tight, the superposition coding strategy. We have this other theorem, which I was going to prove, but obviously we don't have time, which basically says we've got this particular inner bound, and I think I'm just going to be skipping. We're running out of time. Wow, only 4 minutes left in the entire 2-quarter sequence. Okay, so we're not going to prove achievability. What do we want to say here? Well, here's the clouds. This is the same thing we just mentioned. So we can use auxiliary variables to sort of prove this without any sort of superposition or successive cancellation, and use typicality theory. We have errors that are bounded, and we show that that works. Okay. Let me just say this. I would recommend, if you're really interested in this, in reading Chapter 8 in Gamal and Kim. That's the great source on this stuff. There's the degraded broadcast channel. When you do have this sort of asymmetry between receiver 1 and receiver 2, you can sort of think of this in some sense as a Markov chain. And you've got another kind of set of rate regions that you can get in different analysis and different coding strategies. Here's the example. So you could think of it this way, or you can think of this as the successive Markov chain. Where first you receive to y1, and then it gets further corrupted to go to y2. And that can lead to some interesting strategies. There's the Gaussian version, where it's basically the same thing, except that everything's done with a Gaussian channel. And we have this Gaussian capacity again coming up. We have this set of rate constraints. And let me just say a few last things about general networks. The general network, and this is open research. It's not, most of these scenarios are not solved. Each sender is trying to communicate simultaneously with each receiver. The X's are not necessarily independent. And what we're sort of trying to do is, we have essentially a set of rates, R of I to J, which is trying to send a message. So we have this set of messages, 1 to 2 to the n R I to J, messages from I meant for J, and we're trying to send all of these things simultaneously over these over this joint channel. I'm going to skip this thing just to sort of show this theorem. One thing we do know about it is that if all rates are achievable, then there is a joint distribution such that this rates must satisfy this set of inequalities. So it is sort of a polyhedral inner bound of the achievable region of the set of rates. But we really don't have a good characterization of the frontier. And people are continually trying to get tighter outer bounds and tighter inner bounds, sandwiching ever tighter this frontier. I'm out of time. I'm going to skip all of this stuff. Multiclass channel. Anyway, I want to say one last set of few words about the class. So I would recommend, if we don't have a network information theory class, this is you can lobby for this. You can sort of send mail saying you loved information theory too. I wish there was an information theory 3. But if you don't have this, I would recommend everybody should buy this book, the Gamal and Kim book. I've drawn from it heavily over the past couple of lectures. It's a really nice book. It's a really good read, and it has a lot of information in it. It's very comprehensive. It has some stuff in the introduction. I still prefer Cover and Thomas for the introductory material, but it's a great 3rd quarter sequence, I think. If you're interested in machine learning and graphical models, there's a lot of relationships between the information theory and network coding and belief propagation and graphical models, which goes back to results from Gallagher in the 1960s for doing coding theory. So So coding theory is very similar to sort of inference in probabilistic models. And strategies for doing that gets really into inference on graphical models. For optimization, there are a lot of the bounds that we started looking at get into sort of discrete and combinatorial optimization. And there's a fantastic book by Alexander Shriver. This is a 3-volume amazing set of book on combinatorial optimization, and I would recommend looking there. And for generalizations on information measures, you can talk about, you can discuss submodular functions. Oops, what did I just do? I just went way back to the beginning. That's not good. There we are. And then for various applications, if you're interested in information theory for applications, there's no substitute but to learn about these applications. If you're interested in speech, you should learn about speech. If you're interested in bioinformatics, you should learn about bioinformatics. So that's basically the course. I hope you've enjoyed it. And I hope somebody understands everything. I'd be very impressed. Thank you very much.